what I want to do is just kind of get an overview of the entire course. Just kind of remind you of where we've come from and where we got to. Okay, we began innocently enough with just an attempt to characterize logic, and the way we did that was to say that logic amounts to the study of the formal structure of reasoning, trying to identify what reasoning is like, natural reasoning, and indeed trying to find an ideal form to which, efforts at reasoning, our own and the efforts of others, could be compared. One can use this sort of material to sort of critique the arguments of other people, or to sort of critique your own arguments and try and see, whether they are really, whether the reasoning is really valid and sound. And toward that end, we broke out a few pieces of jargon. An argument in this course is just a collection of statements, some of which are given as reasons for other members of the collection. Arguments aren't necessarily combative. They're not things that have any emotion attached to them. They're just lines of reasoning, and so that's all we meant by argument. We talked about breaking arguments into a standard form where we would distinguish the premises from the conclusion. All of these as part of our efforts to sort of give some sort of formal structure to the reasoning process. We introduced terms like validity, and our very first analysis of validity in sort of natural terms, vague as they are, we said that an argument is valid just in case it's impossible for the conclusion to be false if the premises are true. And that's a condition on validity, and I say that it's sort of vague because it uses this word impossibility. So what do we mean by it's impossible for the conclusion to be false if the premises are true? Well, at that particular moment, there wasn't much more to do but just sort of use Venn diagrams, so I sort of sketched to you this particular line of thought, where if we represent categories by circles so that everything inside this circle belongs to the category P, pretzels, say, so that all pretzels are to be imagined as being collected within that circle, and then everything outside the circle is the world of non-pretzels, non-P. Well, then Venn diagrams allow us to sort of express sentences such as all twisty pieces of dough, call that T, all twisty pieces of dough are pretzels. I guess they may not be, but that would be the sentence. The way to express that sentence is just to say the entire category of twisty pieces of dough is included in the larger category of pretzels. To express sentences like that just says, to say that an argument is valid is just to say, and let's just say snack foods. S is snack foods, so if we say all pretzels are snack foods and all twisty pieces of dough are pretzels, the sense in which it's impossible for a conclusion of an argument to be false if the premises are true is represented by these circles. So if I say, if I try to conclude from my first two sentences, namely all pretzels are snack foods and all twisty pieces of dough are pretzels, if I tried to conclude from that all twisty pieces of dough are snack foods, that argument anyway is valid, whether or not it's sound. The impossibility of the conclusions being false is represented here by the fact that just representing the first two sentences already embodies the truth of the third sentence, namely the conclusion. The conclusion's already up there. I haven't had to add any information. All I had to do is the diagram in this format. I had to diagram the first two sentences. The third sentence is already there. So I'm not adding any information. Even the word inference is kind of misleading because I'm not going from someplace to somewhere else. It's already there. And indeed, all valid argumentation really just amounts to unpacking whatever's already in the premises. Nothing new is added. So at that point, I had to sort of wave my hands in this way and draw these funny pictures in order to describe what validity meant. An argument is valid, though, we concluded, just in case it's impossible for the conclusion to be false if the premises are true, indicating that word, trying to illustrate that word impossibility by these diagrams. Arguments are invalid just in case they're not valid, which is reasonable enough. And then distinguished validity from soundness, where soundness included not just validity, but it requires that the premises of the argument be true. Like, I'm not at all sure about all twisty pieces of dough being pretzels. Seems to me like maybe they are, maybe they aren't. I don't know how pretzel is defined. I'm not really, haven't gone into that a lot. One could probably look at, I see Jesse nodding his head back there at me, so maybe he's just checked it out on Wikipedia. But what do you know about pretzels and twisty pieces of dough?
I was just agreeing with the...
Not knowing. Good. Yeah, because I can't be sure about the soundness of this argument. I can be sure, though, about its validity. Yeah, Jess?
Now that I think about it, challah bread.
Yeah, challah. And that's not at all, that's not a pretzel. That's a twisty piece of dough. So surely that premise at least is worth looking into. I'm not sure that it's correct. All right, so we distinguished between validity and soundness. That stuff was pretty clear. And finally, when we got to our sentence logic, we built it out of atomic sentences, which were just the capital Roman letters except for V, a set of simple connectives, which are listed there, ampersand, vel, or V, the horseshoe, triple bar, and the tilde to represent not, and finally parentheses, which allow us to group stuff. So that was the very basic equipment that we used starting with sentence logic, actually trying to move away into a more formal system away from the very basic elements of logic that we began with. So this is the first step towards something a little bit more precise than our just general vague notion of natural reasoning and natural logic. We talked about truth conditions and began to build truth tables in which we could sort of assess all the logical possible combinations of truth, given that these capital letters generally refer to sentences. The P and the Q are variables for sentences, which might be atomic or they might be molecular. In other words, they might just represent sentences like A, B, or C, the same sorts of sentences that we diagrammed here with our Venn diagrams. But they need not. It could be that P or Q might represent a conjunction or a disjunction or an implication or an identity statement. The P's and the Q's are variables for sentences, whether they're atomic or whether they're molecular. And then they, too, can take places in larger sentences that you might conjoin with an ampersand or disjoin with a V or involve in an implication with a horseshoe, etc. So the basic truth conditions allowed us to construct truth tables, which is one step forward toward figuring out just exactly what do we mean when we say that a sentence is true. It's to say that now its truth table on a particular line, under a particular interpretation, a particular assignment of truth values, namely true or false, that the whole sentence comes out true on that line. And then we further were able to define several other concepts which were basic to our understanding of sentence logic. We talked about sentences being logically true, and that's in the case where the truth table of that sentence has no line on which the main connective is false, so that all of its lines, all of the possible combinations of truth values of its components yield the main connective being true in every single line. That's a logically true statement. And a sentence in SL is logically false if there's no line in which the main connective is true. In other words, it has all F's. So those were those two. We talked about logically indeterminate sentences, which naturally enough are ones in which you find both T's and F's on the various lines of the truth table for its main connective. And two sentences are logically equivalent when they have the same list of truth values on their two truth tables. That is, if there's no line on their joint truth table where the main connective of one sentence is true while the main connective of the other is false. They have to have the same values from one to the other. So these are our understandings of those several concepts. We also talked about sets of sentences being logically consistent. And all that requires is there's at least one line on which the main connective of all members of that set of sentences is true. One line on which all the sentences could be true. You know, you've got a massive truth table with a number of sentences, and you look at the main connectives of each one, and if there's some line, all you need is one. If there's one line on which all the sentences come out true, then that shows that the set is consistent, at least. And it's inconsistent if there's no such line. And now, getting back to one of the things that we defined a few moments ago in our more natural reasoning, we now have a new, slightly more rigorous definition of validity. An argument is valid in SL just in case, and we're no longer talking about vague impossibility here where I have to wave at Venn diagrams. We now have a more rigorous way of formulating that. An argument is valid in SL just in case there's no truth value assignment, that is, no line on the argument's truth table, on which the conclusion is false while the premises are all true. That's our new definition, or was our new definition in SL of validity. So now we've got something more precise to work with. We can actually set out the truth tables for a particular argument, and we can actually see. We can just consult the truth table and determine with certainty whether the argument is valid or not. And it's valid when there's no line where the premises are all true and the conclusion false. And then invalidity is defined in a corresponding way. And we then began to talk about quantification in a kind of a roundabout way. We didn't have too much facility to work with that, but one way of talking about whether a particular quantified sentence was true was to just actually use the brute force method. In translating sentences, just try to see, to write down a disjunction of the representations of the rows of the truth table of any sentence that made that sentence true. And just sort of say, look at line 1, if that's one of the ones where the sentence came out true, say that or that or that for the three different, let's say the three different possible lines where the truth table came out true. That's one way of formulating quantification, but a very clumsy way. We developed all of these several by now familiar rules of inference, derivation rules for SL. All of these being pretty straightforward, and I think they offered no particular difficulty. We talked then, by way of providing a bit of an introduction to more formal quantification, we talked about conditional proofs, which are ones where we make an assumption to see what can be derived from that assumption. And we utilize the technique of subderivation in the Logic Cafe. There's other ways of doing this using other logical systems and other formulae, but in the Logic Cafe they use subderivation, where you actually bring out the assumption that you make in your conditional proof, bring that out into a different column. You're obliged then to discharge that assumption before coming back to the main line of the derivation. In other words, one interrupts the main derivation with a supposition of some kind, which then facilitates the conditional proof, gets you to some conclusion or another that gives you some sort of informative information. Usually it's information you're looking for after having consulted the conclusion, that the thing that you're trying to get to. What do I want to get to? That gives you information about how to construct your conditional proof. And that led us to the various rules that could be applied within subderivations, and there were just three: horseshoe introduction, tilde introduction, or tilde elimination. Now, that was a more or less stable moment in the quarter when we had gotten through sentence logic. We worked through several derivations there. And once we'd gotten used to that equipment, we made one further step, which was fairly significant. We went into predicate logic. Predicate logic is different from sentence logic, although it keeps allowing sentence variables. So whenever you saw a single consonant, not counting V, if you saw a single consonant in the formula not associated with any little names as arguments, that continued to represent sentences, atomic sentences, SL sentences, if you like. But we now added a new facility in order to allow a distinction between the subjects and the predicates of sentences. That's why it's called predicate logic. And to characterize relationships among things like older than, before, the sum of, things like that. And eventually came to allow us to characterize important quantificational features of sentences. And by that, of course, I mean the new functors that we got later on of the universal and existential quantifiers. But at first, all we did was to break sentences down in such a way so that we could see the subjects and predicates and see the logical relationships that were packed into the internal mechanism of sentences. Then we finally came to existential quantification. This is an example of that, where, for example, if the universe of discourse is natural numbers and the names for the numbers are A, B, C, etc., and if we use LXY as the relationship, X is less than Y, then the way that we would say that there's a number less than 3 is EX LXC. So that was a new piece of equipment, and of course then there was also universal quantification, where we were allowed, in this case, the same universe of discourse, the same naming convention, the same less than relationship, but where we use EX to represent X as even. Then the way to say all even numbers are greater than 1 is to say for all X, if EX, then LAX. And LAX means that A is less than, A, namely 1, is less than it. So for all X, if X is even, then 1 is less than it. So that's the way to put that, using those simple predicates. You could, of course, have had a greater than predicate, which might have simplified the matter further, but that's just an illustration. And then finally, we had to leave the realm of truth tables. It was before we had gotten a slightly more sophisticated understanding of the meanings of sentences and how to understand when sentences are true and false, and we'd use truth tables for sentence logic. But truth tables won't work, especially when it comes to universally quantified sentences that have as their universe of discourse an potentially infinite number of names, like the natural numbers. If that were our universe of discourse, we would never get off the ground in trying to develop a truth table for universally quantified sentences. So we need a different way to understand the interpretation, the meaning, or the semantics of these sentences, where semantics before was done in terms of truth value and in terms of truth tables. Now we have to find a different means in the predicate logic, just because our equipment takes us beyond the bounds where truth tables can be constructed. So an interpretation is something where we establish a universe of discourse, and we mention the members of the universe of discourse to which any one-place predicates apply. And it includes relationships between members of the universe of discourse to which any two or more predicates apply. and then the truth value of any zero-place predicate letters, which are, of course, the atomic sentences. So there we're still, the interpretation of atomic sentences is still going to be T or F, truth values, the same interpretation that we gave when we were just talking about sentence logic alone. And then finally, where the interpretation in PL will specify the objects named by any individual constants. And so here's a very, very simple interpretation. That's what we did here, where the universe of discourse is natural numbers. There is the specification of the names, of the naming convention for individual constants in that in this universe of discourse. There's a two-place relationship, namely L, which is the less than relationship, and a one-place predicate, namely being even, that is named there. So that is what's meant by a PL interpretation. That's an example. They can get as complicated as you please. We also had to talk about substitution instances in that context, where what we mean by a substitution in sentences is a situation in which we have any kind of quantified sentence, like all x p, where p is a variable that can conclude the most complicated sentences you please, but as long as it's a well-formed sentence, it counts. Or exists xp, where the existential quantifier is the main connective, which dominates the sentence. So take any sentence like that, any well-formed quantified sentence in predicate logic. A substitution instance is just the result of taking P and replacing every occurrence of the letter X in it, given that X is the variable that's being quantified over, replacing every occurrence of X with some name, A, for example. So that's all we mean by a substitution instance. So given the idea of an interpretation, the idea of a substitution instance, what we are led to are the semantics of the predicate logic. And so now we can interpret what it is to say that a sentence in predicate logic is true, and we break out the universally quantified sentences of PL and the existentially quantified sentences of PL in this way. All XP is true on an interpretation, call it I, if and only if the substitution instance of A for X in that sentence is true on that interpretation for all names A. And similarly, EXP for any sentence, however long and complicated of predicate logic P, EXP is true on an interpretation I if and only if the substitution instance of A for X in that sentence is true on that interpretation for at least one name, A. So no longer do we have to use truth tables to sort of determine the semantics for our system. We're given a new interpretation which corresponds to the new complications of the different kinds of quantifiers. And accompanying the new connectives, the new quantifiers, we also got some new derivation rules. Universal elimination, existential introduction, universal introduction, and existential elimination. For all of the connectives that we've had, of course, we need both introduction and elimination rules. The first two of these, all E and existential I, those are pretty straightforward. They didn't require any new equipment than what you had before. You could kind of just see how those worked. The second two, universal introduction and existential elimination, were a bit more complicated. I think I would say the last one, the most complicated of all, just to sort of see its logic. So that required a bit more work. And they went like this. You'll remember universal introduction says that you can go from a formula that's unquantified and contains the letter A to the universally quantified version of that sentence, which replaces the A's with X's, if the A in the original sentence is arbitrary. And by arbitrary, we meant first of all, it didn't occur in any premise. And secondly, it didn't occur in any undischarged assumption. And thirdly, it didn't occur in the particular line derived by the use of universal introduction. The statements of these rules, existential elimination even more so than universal introduction, the statements of these rules is extremely complicated, and once again, the most useful way of becoming familiar with and comfortable with these things is just to do the exercises. This is supposed to be a schematic illustration of the deployment of existential elimination. If you have a premise, existentially quantified sentence, any sentence, however long, in the predicate calculus, where x is a variable and the existential quantifier is governing that whole sentence, the way to break that out, the way to eliminate that and make use of the information that's embedded in there is to, well, take as an assumption, not on the line in the derivation, but take as an assumption a particular instantiation of that sentence. This is said to be true. That's a premise. So you say, all right, well, give the variable a name. So you break away from, you eliminate the existential quantifier in your assumption and see what follows from that. And usually you're looking for something that will get you toward the goal that you're supposed to achieve or that you want to achieve, the thing that you're trying to derive. And then there's some number of lines, 3 through n-1, that it will take you to get to whatever conclusion you're trying to establish. And then on line n, you finally get it. Let's say it's q. What you're entitled to do, since this was an arbitrary name that you assumed, you just called the thing over which the existential quantifier was quantifying, you called it something just for the sake of this argument. Since it was totally arbitrary, just illustrative is the word that the cafe uses. It was an illustration of the things or thing that you know have this property. Since that was completely illustrative, then you're entitled to establish Q, because you know that there's something of which this is true. You've just given it an arbitrary name just to see what follows from it. You've established that Q is the case, so therefore you're allowed to bring this very conclusion, the very thing that you've proven here, bring that back into the main derivation and use existential elimination using line 1. That's the thing from which the existential quantifier was eliminated, and 2 through n, that's the conditional proof, the subderivation in which you've demonstrated this conclusion. You can just drag that back on line n+1 and state it as q. Now that's a long-winded way of trying to explain this, but that's probably about the best you can do with these provisos that A is illustrative in this sense. It doesn't occur in any undischarged assumption. It doesn't occur in the P that you're trying to you don't want it in the premise. It doesn't occur in the P that you're deriving it from, and it doesn't occur in the Q that you establish as your conclusion. If that's the case, then that A is illustrative in the desired sense, and you can use existential elimination. Now those were fairly complex to describe and pretty complex, I think, to get used to, judging by your experience, with trying to work on those things. But I think most of you finally figured out how we were working with it. One of the big problems was to try and figure out, well, what is it that the existential elimination is? Where is it eliminating an existential quantifier? Well, it's from this. It eliminates this in the very first step, in the assumption. It says, all right, let's get rid of that existential quantifier and just treat this as if it were a sentence that had a name in it and see what conclusions can be drawn. So that's where the existential quantifier was eliminated. That's why it gets specified. That particular line that was existentially quantified, that's why it gets specified separately before the comma. And then these lines here were the ones where you actually did the deriving. But that was one of the problems that some folks had, and this whole business of trying to drag the conclusion here bodily back to here, that's confused some people as well. So I'm hoping that by now you've gotten fairly comfortable with it, but that's a permissible technique as long as these conditions are satisfied. And then the last rules, this one was a transformation rule for predicate logic without identity that we had was just quantifier negation, which was, I think, pretty transparent, pretty obvious once again. It allows you to move negation signs, tildes, around in quantified sentences for better facility at being able to unpack the things that you want inside these formulae. All right, that equipped us with full-scale predicate logic. And all that we added to that in the most recent weeks is the identity relation, where I is reserved for now, the capital letter I is reserved to mean the identity relationship, at least where it is followed by two arguments, two names. We are instructed to use I always for the identity relation, which has its own internal logic. Once again, we're doing some packing. I think what you see is a consistent theme here. We start off with something that's big and intuitive about what makes a logical argument valid, what makes it a good argument, and we try and get more and more precise. And one of the ways we get more and more precise is by unpacking things, from going from sentence logic, which just talks about big sentences. We break those sentences down and try and see some of the logical relationships within sentences, and that gives us predicate logic. And now with the identity relationship, we're trying to break down some relationships, in particular this identity relationship, to show what what the internal logic might be of that structure. So with identity comes several rules. We symbolize identity this way so that we, for example, say Sam is the person on the phone, might be symbolized ISP, and it comes with its own set of inference rules. One is reflexivity, which says, and this is a very valuable rule for lots of purposes, at any point in an argument, at any point at all, you can simply introduce the sentence IAA for any value A, or IXX for any variable at all. You can simply introduce that because everything is identical with itself. That's just a logical truth. That's an internal logical feature of the identity relationship. So you can always introduce any IAA on any line of a proof without any premises at all. Symmetry suggests that the identity relationship can be flipped around. So IAB equals IBA. Transitivity, if IAB and IBC, then IAC might remind you of the symmetry of the logical relationships of the horseshoe that we covered earlier. And then finally, substitutivity, which suggests that you have any formula with A in it, and then you know if that A is identical to B, well, then you can replace that first formula with the same by substituting B for every instance of A. You have to be careful to make sure you do every instance, but you're entitled to do this. So with these rules of inference, we had our complete system of predicate logic with identity. I want to talk a little bit about where we didn't go. I mean, I offered you a couple of, as I say, baby steps toward seeing how logic, which we've now developed out of sort of intuitive reason, intuitive principles of natural reason, that our formal system might provide a basis for mathematics. One might hope, since mathematics seems eminently reasonable, one might hope that you could use these simple principles to provide a basis for all of mathematics. But that's just one of the sorts of applications one can make of logic. Artificial intelligence, for example, insofar as it makes use of computing apparatus, makes use of this very same sort of principle. Maybe not exactly with the kind of notation we've used, but the whole idea of trying to understand the structure of reasoning is mimicked in the computer world by trying to build or conceive of, anyway, even if it's just an abstract artificial machine of the kind that Turing was imagining. Just trying to figure out how, in principle, one might build a machine, whether or not you have the technologies available to you, how, in principle, you might build a machine that would sort of seem to express some of the basic ideas of intelligence. I mean, that is what artificial intelligence is all about. It tries to figure out how to mimic reasoning, how to mimic rational processes. So there's a lot of common ground between the study of logic and the study of artificial intelligence. In particular, programming languages have grown out of logics and have developed their own vocabularies and their own elegant ways of proceeding toward their goal, namely of trying to sort of design machinery that accomplishes tasks that are ever more complex. In neurophysiology, trying to see how the brain itself mirrors some of these logical principles is very interesting. One can even imagine that whereas on and off in the world of computers can simulate truth and falsity. Similarly, in the world of neurons firing and neurons not firing, and neurons getting to a potential where they can fire and where they can't fire. Those are all another way of interpreting or another application of truth and falsity, of on and off. So, and then, as you can see, the world of neurophysiology, which tries to examine how brains work, and the world of computers, which tries to build machines that are going to do something like what brains do, all of that stuff is kind of, intermingled. And the philosophy of mind, which has its roots in trying to decide, in old questions, ancient questions, like, is there such a thing as a mind that's distinct from the brain? Is the body and the mind, are they the same things? Those are old questions that go back thousands of years, continue to occupy philosophers up through 300 years ago. But even by the time of Descartes in the 1600s, Descartes was already talking about trying to develop artificial intelligences of some sort. He talked about pneumatic devices that would be run on water power and water pressure. And he imagined, and actually that was an interesting technology that arose in the 17th century in people's gardens, little things that sort of functioned like robots, and they were pushed around by water pressure, but still trying to figure out exactly how to get those things to move and work, and what the difference between those little robot-like things was and human beings who could think. That's part of what animated Descartes himself 300 years ago, trying to figure out, well, what's the distinguishing feature of the human mind that makes it different from all of these things that imitate activity in some way or another. Well, those are the old questions. Nowadays, philosophy of mind, done in philosophy departments all over the world, really can't do its work without taking into consideration some of the work that's been done in artificial intelligence and neurophysiology. But it's all Bollock stuff. This whole area is called cognitive science. And the work of logicians, the work of computer scientists, the work of neurophysiologists, all feeds into this area of cognitive science. It's a very rich area. And its ambition is the same as ours has been. Its ambition is to figure out what is the structure of reasoning. Sometimes it's the logical, formal structure. That's our business. Sometimes it's the material structure, like how do computers work? How can we make them more like human beings? Maybe one way of doing it is to sort of build whole networks, artificial networks. Of computers that sort of learn from their environment in the way that organisms do. That's been a very promising road that artificial intelligence has taken. But they're trying to figure out ways to embody in silicon, usually, but to embody the very processes that we've been talking about in a particular medium, silicon. And then the neurophysiologist's work is to try to report and to examine how it's embodied in soft tissue, in wet tissue, in our brains, in our minds. And then finally, you can imagine that there's a whole different kind of world of applications that's is made of logic and rhetoric, the study of ways of delivering ideas in a convincing fashion, of ways of appealing to people. So that's another further development that one could make of our logic. So that's where we were, and that's where we've come to. I kind of thought it useful to sort of bring it all together so you can see what we've done. It's been a busy course, I think, for all of you. Some found it a little easier than others, but we're now at a finishing point. I wonder, are there any questions or comments that any of you might have before we close out? All right, well, live long and prosper and have wonderful lives.